Morning. Thank you very much. Thank you for inviting me. Pleasure to be here in Shenzhen. And I look forward to talking to you a little bit about where we are with service computing and where we are going and what the kind of the state of the world is. So let me start by reminding everybody that this is a kind of a old discipline now. So the modern era of services started with the release of the SOAP specification. That was in 1999. This was an email that was sent at that time by a guy called Dave Weiner. He was one of the people who were behind that work. And there was something called XML RPC before that. And so what that shows you is we are now literally 25 years later that we are talking about this, right? But of course, services didn't start with SOAP. The concept of services predates SOAP. So just to remind everybody, before that also we had services, except they were less interoperable, more tightly coupled. So we had something like CORBA, for example, which required the same software to be available on both sides. There was a version 3 of CORBA called IIOP, which was trying to address that, but by the time that became supported, it was kind of too late because there were less heavyweight solutions coming along. Then there was Java, where you could do distributed computing with Java, but again, it required the same language on both sides. And DCOM required DCOM on both sides. So, and also, if you go back even further, go back to a mainframe, CICS transactions are actually a services model. They have the same life cycle, same kind of protocol, and it required the same language and same platform on both sides, right? So it's been around for a while. So the difference with the second iteration is really the focus on interoperability. Interoperability meaning instead of saying, how do I communicate between two systems which are under the control of the same person, communicate with something on the other side, I don't know what it is, and I focus on how do I express what I need to send and receive. Right? And there's a golden rule on the internet which roughly reads, you should be rigid about what you write, so follow the schemas, follow the protocols, follow the standards very strictly how you write something down, and be very flexible about what you read. So support people who haven't got it right, but be very strict about what you put out. And that's really the foundation of many of these sort of interoperable service architectures that we've had. And this started with SOAP 0.9, and then there was a spec called WSDL that was done right after that. And of course, things have evolved. Nobody uses SOAP and XML anymore. Now it's about JSON and REST, or GraphQL with protobuf, or et cetera, right? So there are lots of different protocols, lots of different ways in which you can do services, and things have evolved and become more mature. And actually, we wrote a paper, an article to the CSCM a long time ago, in 2002, which talked about this concept of enterprise services spanning different protocols, going all the way from CICS transactions to web services to other kinds of services as well. So this stuff has been around for a long time with different mindsets. So just to give a little bit of background on my own background in this space, so I was involved with defining most of the specifications. I'm one of the original authors of WSDL. I also worked on the original SOAP spec, did a bunch of open source implementations, and I used to work in IBM research for 8 years. After I moved back to Sri Lanka, I started a foundation called the Lanka Software Foundation, where we did a lot of open source implementation work of various web services standards. And the goal there was to enable interoperability. All the work we were doing was in Java, so that meant the only users of that were for people who were using Java as a programming language. But of course, Java was a very, very broadly used programming language for a very long time. It's kind of declining now, but it's been very popular for a very long time. I was also program chair of the co-chair of ICSOC 2003, one of the earliest conferences on service-oriented computing, which was before the IEEE Services Congress and all this work started, actually. So I've been involved with this stuff for a long time, which tells you that I'm very old now. And also, I started WSO2. I just want to talk a little bit about this because it's kind of, again, from both from the scope of work of the company as well as just to encourage entrepreneurship in China. So I'm the founder and the CEO. I'm a technical guy. I don't know anything about running a business. I work on technology. I work on the product and I work on architecture, and we do everything open source. So all of our software is completely open source. Anybody can download it. And over the years, we have built every part of the services software stack. Whatever part you want to name, whether it's hosting services, mediating services, integrating services, discovering services, describing services, every part of it we have built over the years. And we've evolved the technology stack as time goes along because we've learned what of those are actually practically usable. For example, yesterday, Marco was talking about the service registry not really working out, and it was a big area of investment for a long time. I can certainly confirm that, and various other parts that over the years. The company itself is about almost 800 employees now. We have customers in 94 countries. All of them have come to WSO2. We don't directly sell to the customers. They find out about the product, they download the product, or they come to the website and say they want to work with us. And we are about just almost $100 million ARR company. And 80% of the employees are actually in Sri Lanka. So a enterprise software technology is something that anybody can build. And when I started the company in 2005, there was a general mindset saying, if you're going to build an enterprise infrastructure company, you must be in California, or you must be in the US at least. And I had lived in the US for 16 years. I didn't want to go back. I said no. And we built the company. It wasn't easy, but it was possible, and it was done. So I think even in China, actually, WSO2 products, #1 download country is China. About 50% of all our downloads come from China. So there's a lot of wide usage, but we don't see any competitors in any of the spaces we operate in from China. So in the enterprise infrastructure space, in the global market, I think in China, probably it's very different. I think there's a lot more opportunity for software companies from this side of the world to go to the world market, create products, and challenge the market because there's so much potential in this area. So let's come back to the topic. So my topic is really asking the question, we've been around with this services computing stuff now for 25 years. Are we there yet? So really, if you go back, so to answer that question, you must ask, what is the problem we are trying to solve? That is my favorite question, by the way. What is the problem you're trying to solve? Because if you don't know what problem you're trying to solve, you don't even know when you've solved it, right? You have to be clear about the problem. So what is it really about? Why are we doing services work? What is the motivation for it? What is the problem you're trying to solve? So fundamentally, it's related to reusing via network calls. Right? Service abstraction is a way of saying I have some capability that somebody else can access it and use it in some fashion. And of course, there are many good reasons why that's very useful. Everything from, hey, if you can do it for me, I don't need to worry about it. I just send you my request and you do it for me. And the services software abstraction comes from the service abstraction of the economy. In the economy, we outsource a lot of work to somebody else. We pay somebody and saying, hey, do this for me. You give them a request, and they do it, and they send them back the response. And that abstraction is what we are creating within the software universe. And it makes it much easier because you can focus on the parts that you need to focus on. You can ignore all the parts that you don't need to work on. Just focus on saying, hey, if I give this kind of abstraction, I get that kind of response back. Right? And of course, that introduces new problems. So you have security problems, availability, reliability, cost, all kinds of things that you do need to worry about. But fundamentally, it's about reuse and making things better. But the reuse problem actually has many solutions. And reuse is one of the critical enablers of high-quality software engineering. And there are two fundamentally sort of different approaches ways in which you can reuse the work done by somebody else. One is, of course, to get at the code. If you can get at the source code, you can reuse somebody else's work. And that can be done in multiple ways. Just keeping track on time. That can be done in multiple ways. So if it's source code, you can just download the source code from something, and that's what open source has thrived, where somebody can download code and incorporate it. With technologies like GitHub, it's become very, very easy to take somebody else's code, make a copy of it, make a modification, keep the modification in sync with the original one, and keep evolving it, and so on, right? And of course, you have binary libraries. In the Java universe, you have Maven Central, you have NPM, you have pip, you have all these different platforms for how you share code between different implementation, different users. And that's great, but very language specific, of course. And the other one is you reuse via capability, which is where services come in, where the goal there is instead of reusing the code itself, you don't know what language it is written in, you don't know anything about it, you just know what it does, and you reuse the capability. So, sorry, wrong button. In fact, this is a slide from a kind of old presentation from CMU about the product line architectures work. And what this talks about is different styles of reuse that have been around for a very long time. So if you go back to the invention of subroutines in the 1960s, then to modules, objects, components, and services, it's sort of the latest incarnation on that evolution of reuse. Of course, services is different from all the others because all the others were language-specific solutions. Whether it is components or modules or objects and so on, they were all specific to a particular programming language or a particular development environment in which you were able to operate. Services takes it a lot bigger step because you no longer rely on the language, it's just over a network call. So of course, one key thing is to make something work in a reusable way. For me to reuse something you did, it must be something useful. So getting the atomic architecture right, or the components that I'm going to build on, getting that right is not easy. It's an art form, it requires judgment. So just if you look at two examples, if you look at linear algebra, if you have a basis for a vector space, then you can get to any point in that vector space. You just need that basis. Of course, if it's orthogonal, orthonormal, it's even better. But if you have a basis, you can get to any point in that vector space. So from that point of view, the basis, any basis becomes a way in which you can reuse all points in the vector space. So similarly, in chemistry, atoms combine into molecules and compounds and so on. And if you don't have the right atoms, you can't have the right molecules. So things like service composition, which is a very important area of research, for that to work effectively, the underlying components you are composing must be at the right level of granularity, right level of abstraction, right level of reusability. Because otherwise, you end up in a big mess. And in software engineering, if you look at the problem of reuse, there's been, again, many technologies for reuse at the code level primarily. So whether it's objects and classes on one side, and then modules and various kinds of things, and different languages have invented different solutions for how you do that. But the technology stack is quite effective, yet the quality of software that we produce and the ability to reuse is still very limited. The reason being that the ability to get those units right is still an art form. And getting that abstraction correct so somebody else who you don't have any contact with can find this software useful is really quite a challenge. I can't remember who it was. One of the Java architects had written a blog a long time ago saying, if you want to get an API right, a Java API in that time frame, you need to write the API and then use it, have 3 independent groups of consumers use it and find that the abstraction is right. That's when you know you've got something that can potentially be used by 300. Right? Otherwise, you've got something that works for this person or works for that person, then the reusability is far less. So that's an art form that we have to crack. And so really getting the service abstraction right is fundamentally key to getting reusable services. So let's talk a little bit about abstraction, because abstraction is one of the most important principles of computer science. And in fact, the way I explain computer science to somebody who doesn't understand computer science is just say, computer science is really all about just abstraction. It's about finding a way to represent a problem in different ways, in an abstract way, so you can solve it at that space and then go back and solve the actual problem. Right? Abstractions are powerful because you can ignore lots of details and think without going into the detail, think at that abstract level, and then do whatever you're doing at that level, and kind of magically works down below. Right? So there are many amazing abstractions that have been developed in the history of computer science. Abstract data types, Barbara Liskov. Then we have data persistence. The entire relational storage model were very, very fundamental, had a huge impact on so many different systems. And Kubernetes. Kubernetes is not Turing Award level yet, but I'm pretty sure it will get one because it deserves one in many ways. And if you look at Kubernetes, what it abstracts is essentially hardware, and it gives a set of abstractions using these 6 terms, these 7, but sort of six concepts. And of the 6 concepts, you only have to pay attention to 3 of them if you're a developer. The others are there. You need to know they're there, but you don't even have to worry about them. And with that, you can build scalable software systems that work in a distributed infrastructure, that run on different computers, physically separated, geographically separated, and everything just works with those abstractions. Right? So the point is, if you have the right abstraction, it dramatically changes the domain. It's not, if you look at all the 3 examples I gave, they don't just make things a little bit better. They dramatically change how you think about problems in that domain, right? And how you can do things with it. There's something called the fundamental theorem of software engineering, which is kind of what we do when you build any kind of large-scale system, that you just put another layer of indirection, and that's how you solve the problem. You put a interface, and then you solve that problem. Of course, except for the problem of too many levels of indirection. But abstractions are not just indirections. To be a great abstraction, you have to go beyond just indirecting to something else, but you need to change the way somebody thinks about the problem. Create a new mental model, and create a new mental model for how you understand the underlying concepts, express them, and so on. Otherwise, it just becomes a least common denominator, right? And least common denominators are useful for many things, but they're not abstractions. They don't change the fundamental problem or make it easy to do things. So again, coming back to services computing, why are we doing this? So in the end, people build applications. The things that pay for all the work one way or the other are somebody buying some software at somewhere down the road, maybe 10 years down the road, 20 years down the road. So these applications are enterprise applications. So I just want to talk a little bit about that and understand the state of the universe of enterprise applications. The reality is that the answer to this question is absolutely no. Right? Most people, there are exceptions, but in general, people are still not able to produce software, quality software, on time and within budget. You lose one of these 3 things for sure. You either blow the budget, it takes longer, or you have bugs. And the reason for that is the underlying engineering disciplines that we are using to build software are not at that level of sort of maturity, capability, scalability, and reliability, so that when you start writing a system, things just continue to work, and they work as you scale up. The reality with enterprise software systems is that the amount of money that's spent versus the outcome you get is very, very disproportional. In most industries, majority of software projects fail. And these are projects that end up using tens and hundreds of millions of whatever currency you want to use. And they all end up having an unsuccessful outcome. And there are many reasons for this. And on the other side, security, software security, everybody is very aware of software security. It's a big problem, and every day, almost, or at least every week, we see a report of yet another big break-in and a loss of a lot of data. And for every report that we see of a big break-in, there are hundreds to thousands that you don't see because they're too small to be noticed by the press anymore, right? And there are many others that happen where you just don't even know you've been accessed in some illegal fashion. So at the same time, there was an article written in 2011, now 13 years ago, by Mark Andreessen, who was the guy who started Netscape, Mosaic before that, and now runs Andreessen Horowitz, about this concept called software is eating the world, which was a really good article. And so software has been eating the world, but enterprise software engineering is in really bad state yet. And at the same time, software has eaten modern enterprises. There is no such thing called an enterprise that doesn't live without software or live on software. And more what's happening is that almost every company is moving all their functions to some kind of SaaS solution. All the vertical functionality is from some SaaS solution. Private data centers are diminishing. We are going to more somebody else managing it, some kind of a cloud infrastructure, a lot of security and so on. But yet, everybody has to build something for themselves. So even if I use all the available SaaS systems, they all live in their own little vertical universe. So if I want to do something that crosses all of these things, I need to put it all together. And to put it all together, I have to write some code. And these, in modern world application architecture, this would be called cloud native applications because they are designed to run and operate in cloud infrastructures. And that has some certain implications, of course. So these are some numbers from various studies. Every company on average now uses 130 different SaaS applications. WSO2 uses close to 75 different SaaS applications. We don't have anything we run in-house. Everything is through the cloud. And most of the time, the internal APIs play a big role in how these applications are being integrated together. So they have various systems that are done. And about half the effort is on building apps for inside the enterprise. Right? So the development and the quality of the applications and the ability to produce software inside the enterprise is a huge differentiator for every company. Because there is this new tagline called every company is a software company, which basically says, it doesn't matter what kind of company you are, you have to build software for yourself. And then the complexity comes from all these abstractions and the things that you need to put together. So let's talk a little bit about enterprise software engineering for enterprise applications. So we are talking about applications and backends, not the infrastructure. So there are also the technologies and the approaches you use to write something like Docker, to write something like Kubernetes, or to write a VS Code or a compiler or things like that. That's a whole different problem, very, very important problem, but typically not done with a services kind of approach. It's much more hardcore traditional software engineering, but Kubernetes is very, very services based. But still, that's not something that every company has to do. I'm focused on the problem that every company has to do, which is build applications. So they build both human-facing applications and headless application. Human-facing meaning there's some kind of a human who's using it, whether it's a web app or a mobile app or through some device or some other form of interacting with an application, maybe natural language with an LLM, somehow a human-facing application. Then there are headless things that wake up at a certain time and do some work and go away. A lot of integration, a lot of workflows do that kind of stuff. And of course, behind that, there are all the backends to make that work. The APIs, the services, the events, all of these things are underneath to make all of those things work. Right? That's the one that we want to be able to facilitate. And when you put those stuff together, these applications become kind of complicated in how they look and how they feel, because there are different parts that you need to put together in order to build these modern applications, cloud-native applications. And also an enterprise, any enterprise deals with three different constituencies. One is, of course, employees. So if you're in a bank, if you're an insurance company, if you're in this hotel, you need a lot of software to operate every part of the business. Those are software systems that have to be built for those employees. Then, of course, there are customers, right? And the customers are twofold. You have consumer customers, sort of end users, and B2B customers, sort of B2C and B2B customers. And both of them are different because B2C customers want human-facing digital experiences. They may want a natural language interface. They may want a mobile app. They may want a web app. They may want some kind of specific devices. Those are all things that are designed for humans to use. And then you have things that are designed for companies or organizations to use, businesses to use. That's the B2B side of the equation. And all of this has to be built on top of the underlying various systems that are in the organization and which span across all of these things. Right? They're not one-dimensional, they span all across everything. So it used to be that building software was quite easy. Waiting for the slide to update. Let's check the Zoom is not. Sorry, I'm connected through Zoom to the projector. So, thank you. So this is a picture of the computer that I had when I was a grad. It's not exactly that computer, but something like this. When I was a grad student in Purdue in the 1990s, I had a Sun 350. It was called lanka.cs.purdue.edu. And that was actually a real name on the internet. You could look it up from China, you'd actually find the IP address. It had a real IP address. And the way you wrote some software and ran it is you wrote code using VI or Emacs or whatever kind of simple text editor, and you type make typically, and make would just take all the software and put it all together, and then you run it. That's it. And you run it on that computer. If you want to run it somewhere else, you either statically link stuff or you make sure all the shared libraries are linking, and you take it to another machine and you run it, and again, it's actually on the internet. These days, the younger people in the audience wouldn't know what a real IP address is. They wouldn't know the difference between a real one and a fake one because they never see one. Right? Nobody ever sees a real IP address anymore because it's just not available for anyone anymore, right? So there's a big, so that's the way it was. It was very, very easy. Of course, very, very complicated at the same time, because if you want to run something for 10 people to use at scale or 1 million people to use at scale, it was very difficult. You had to have a bigger and bigger computer. You had this, various kinds of parallel processors, various kinds of supercomputers, all kinds of complicated stuff was there. And where we are today, of course, is very different. It's a little bit more complicated. There's a lot more things you have to do when you want to take a piece of code and run it. And if you are in the cloud era and you're using Kubernetes and all this cloud native computing foundation stuff, when the picture comes, it looks like this, right? This is the landscape from CNCF. There's a lot of stuff that is available to you that you need to navigate in order to take that little piece of code that you write and get it to actually run. That's the reality of the complexity that's there today in how we build everything. Right? That era of just run it on your machine is over. So what do you need to be a modern digital operation? Sorry, the syncing is a bit slow. So I look at this on two different sides. One is the digital infrastructure that you need, the computing infrastructure in order to develop, build, and operate software. On the other side, the modern architectural principles that you need to have. So digital infrastructure, everything goes from containerization to Kubernetes to serverless, multiple environments. There's a whole bunch of stuff. And this is not a full list even. Right? All of these things you need to, if you're going to build enterprise applications and manage enterprise applications, you have to have solutions for all of these things, all working together into a single whole. On the architecture side, people, there's all these terms about microservices, domain-driven design, API-based development, all these things. And of course, AI is a big part of everything that we do now. And then you have the security aspect is very important, version management important. So there's a whole bunch of things that you need to have operating in the environment in order to be able to create enterprise applications. So one thing to understand is enterprise software engineering is different from some other scenarios for various reasons. The first one is really important. It's immortality. That is, in general, in a business, you write a piece of software once and you modify it for 50 times. Right? So very rarely do you start again from scratch. It's not done typically. You write something and you keep evolving it because the requirements change, the problem changes, the leadership changes, ideas change, the business change, environment changes. You just keep on evolving it. So versioning plays a very important part of how you manage software as well. Reuse is very important because within an enterprise, there are different information domains that are owned by different business units. So you have to reuse. You cannot get access to things that were from a different part. And this is actually a fundamental advantage that services computing has delivered. Because before services computing, if you wanted to get some information from another part of the business, you couldn't get it digitally. There was no way. You had to have a human transaction going back and forth, basically. With service computing, despite all the challenges, you can now have a single application that lets a customer touch all parts of the business, right? Through APIs. So there's a bunch of things that you have to get get organized in order to do enterprise scale software engineering. Those are, so those are the things that we want to see how services computing can help and what the underlying things that we need to have are to make that work. So to me, the way services computing helps is really by understanding that service computing has to go end to end on the service abstraction. The service abstraction starts at the point of you think about writing code. How do I express an idea into code? That's the first place the service abstraction comes into existence, or the design point of saying what is the service contract, what is the interface, and so on. And then I need better runtime abstractions, and I need to improve the entire developer lifecycle. To make service computing deliver in terms of actually being able to solve the problem of how do you build software that works and is available and it's on time and within budget, you need to do all of these things, not just one part of it, and get a development experience for developers to be able to put everything together. Right? So let me talk a little bit about development abstractions. So, oops, sorry, wrong button. So development basically means code, right? You have to write code. And the problem is that code means a programming language is a way of expressing a design that you have in your head into a form that the computer can understand. Now there's an entire school of thought that says programming languages are over, the new programming language is natural language. I think we have a keynote coming up on the state of AI next. But personally, I'm not a believer that we can get to that point, because natural language, whether it's English or Sinhalese or Mandarin or whatever language you pick, is not precise. And for me to write something down that somebody else understands exactly what I meant is very difficult, and that is why these rigorous languages have been developed. So programming languages are a form of a rigorous language which captures exactly what is meant in the syntax, so that once you've written it down, it is what is meant. It cannot debate, did you mean this, did you mean that, right? With English and any other language, that is always debatable. So language really matters. And the way you capture abstractions in the language is that you have to have features in the language that represents the abstraction. When we invented object-oriented languages, there are language syntax and language concepts for things like classes, objects, inheritance. All those things are expressed explicitly in the language. Now, you could, if you're old enough, if you remember the X11 Windows system, the first version of the X11 Windows system was written in C, right? In fact, they had an object-oriented way of writing it. Because, and also, if you've written with C++ code in the early 90s, the compiler you used was something called CFront, which was a compiler that took C++ code and compiled it into C. Right? That was the first implementation of C++. It came from AT&T Bell Labs called CFront. And so people, so obviously you can represent object-oriented abstractions in a fundamental language like C. So you can program everything like that. But then the thinking paradigm that every programmer has to work doesn't fit into that level. So you need concepts in a language that map to the concepts of services computing. And so this is one of the problems that I have been working on for a long time. We started a new programming language called Ballerina. This was started in 2016, so now about 8 years ago. And the purpose of the language is really to look at the network computing aspects or the service computing aspects and bring them to the language itself. If you look at the abstractions that are there for languages for network computing, there's something called BSD sockets, right? If you've written any kind of network program, you use sockets. And sockets are a great abstraction. They just convert network connections into byte streams of some kind. And then you can just ignore the fact that it's a network and build on top of that and build whatever applications that you want. Then we have this concept of stubs and skeletons, which came from the RPC era. And of course, the reality of a network is that there's a lot of things that are not normal about network computing that are normal about in-process computing. There's a famous paper called 7 Fallacies of Distributed Computing, which talked about some of the things that don't go wrong in normal in-memory computing that can randomly go wrong. And the problem is when the language doesn't understand these concepts, the developer who is programming doesn't have the tools to handle the underlying issues with distributed computing. So you need a language that can capture the semantics of service computing into the language. So that's what Ballerina does. Ballerina has built-in abstractions for network services and clients, for, sorry, the syncing is a little bit slow sometimes. Yeah, there we go. It's thinking whether to show it this slide or not. So Ballerina as a programming language has a first-class concept of services, of service typing, of service clients, of service-to-service data. It understands the difference between network data and in-memory data. It understands how to go back and forth between the two. It understands things like configuration management, access management. These are all things that you need to have in order to build a services-based application. And so the language itself has those constructs, so the developer thinks and develops in those terms and simply gets a compiler to do all the hard work of mapping them to whatever the execution environment that it's running on. Right? And so that's development time. But then you also need to think about the runtime abstractions. Runtime abstractions meaning when you have a lot of services in an environment, you have to manage how those services are operating, because otherwise you'll have sort of a Wild West. A service, remember, is a network addressable endpoint. Once you have a network addressable endpoint, if you need to worry about who can access it, how do you protect it, how do you manage when you have thousands of these and so forth. We have customers in WSO2 who have some customers have about 10,000 APIs that they have within their internal system. Now when you have 10,000 APIs, all the problems of discovery, of security, all these are much more compounded, because that means you simply cannot, no human being knows what all these are. Right? The system has to somehow manage everything. So we published a paper a long time ago, about 2022, in 2018, called Cell-Based Architecture, which is a way of managing how you organize code into a concept of a cell, a network cell. The idea is that you have a concept of a cell which isolates a set of capabilities, and the cell has a well-defined boundary. And in the case of a cell, we identify 4 different boundaries. Northbound boundary are things that you can come in from the internet, from external networks. Southbound boundary is when you go out. Sorry, didn't mean to press the button. Oh. I didn't do anything. Okay. Southbound boundary is when you go out to external capabilities, whether it's an API or some other capability. And the east and the west, east is for going out within the network, and west is for coming in from inside the network. So it gives an abstraction for managing a set of capabilities, and inside the cell you have additional componentry that you have that are the underlying components within the cell, but they are managed and exposed outside. Right? So these abstractions are important to help you manage a set of capabilities. So when you think about implementing a system, you don't just say, I have a flat hierarchy of services. Because again, this is a modularity problem. To manage modularity, reuse and modularity go hand in hand. Getting the right abstraction level comes together as part of that. And cell architecture is a key part of making that work. Right? The third key aspect for services computing to get right is really this concept of the developer life cycle. Because as I showed earlier, the way in which we wrote a piece of code and got it to work 25 years ago or 30 years ago to the way we do it now is very, very different. And that has a lot of cognitive load on developers. And when you have a lot of cognitive load on developers, it becomes difficult for developers to create, focus on their software. So we have another paper we published called Platformless Engineering. The goal there is to really get across this idea that the developers who are working on something should not have to focus on the mechanisms and the tools and the environment that I'm operating in. They should be able to focus on the code they write. Because if you're a developer working on building some capability, the one thing that matters the most is that capability. Not how do I compile it, how do I build it, how do I deploy it, how do I operate it, all these different things. And that has 2 parts to it. There's the engineering or the development time, and then the runtime part. Right? So engineering and operations both have to be dealt with when you design that kind of a capability. So we have a product that does this as well called Choreo. Choreo is focused on the entire developer lifecycle from writing the code. So you just write the code. Once you write it, a typical lifecycle looks like this. You have to build it. Building now means building into a Docker image, maybe run various kind of image scans, and then pushing into an image registry. Deploy means selecting the environment, selecting the underlying region, zone, environment that you want to deploy into, and deploying it into that, and so on, right? So all these different stages have to be executed as part of the development management process. And there's no point in every customer, every company figuring out how do I manufacture software. Right? This is the software manufacturing process, not the software development process. When I write a piece of code to take it into production, there's a set of steps in the modern world that everybody has to do. And this is not a competitive differentiator for anybody. If I'm a bank A versus bank B, there's no point in reinventing the wheel on how you take a piece of software and get it in the hands of consumers. That is a well-established process. Now we just give it as a SaaS capability. Right? And to make this work, there's a lot of development management abstractions you also need to have correctly. And these all tie into the services concepts. So you have to organize your work. So there's concepts like an organization has a set of projects. Each project has a set of components. And each component may have one or more endpoints. And the business itself, if you're a large organization, has to be organized into some kind of domains, business units kind of architecture. So each domain may have a collection of projects instead of just one project. You have to organize the network, because if you don't organize the network, everything you put up on the network is seen by everybody else, which is also not good. And you'll need to support discovery and reuse capabilities. And service composition kind of capabilities have to come in at that level. All these capabilities that you create, when you create some new functionality, it goes into a marketplace of some kind, which is then discoverable, and then from which you can automatically compose and create new capabilities as well. So in summary, so the problem that we're trying to solve is the fundamental problem: how do you produce software on time and within budget? This is a problem that isn't solved here, and services is very much the most important fundamental abstraction that enables software engineering to improve significantly. And so that's what we are discussing here. So service computing has really achieved a lot. We are more than 25 years old. We are no longer, no longer a kid now, kind of a young adult age. And at the same time, there's a lot more to go before we can say that building software is like building this building. When somebody builds this building, or in this Shenzhen area, we see an incredible amount of construction and development. There is no iteration on all of those things. Once you build it, it works, basically. Software doesn't work like that yet, for the most part, right? We don't get any of that right. Typically, you end up iterating and iterating and iterating and getting something to work. It takes a lot of time and a lot of money and a lot of effort. And to fix that problem, you need to solve these aspects of the underlying set of abstractions that we use to develop it. And services are the essential ingredient of that. But service computing has to look at the full life cycle of what does it mean to compute with services. Right? Everything from the time of thinking about the problem you're trying to solve in service abstractions, expressing that in code, to getting it to a point where when I'm trying to implement it, finding other capabilities, composing capabilities, to deploying them, managing them, and so on. All of that has to be thought through. And that's where I think there's a lot of research that's left to be done, because a lot of the work that is in the marketplace, in what practicing enterprises do, is far from anything that is mature at this point today. So I'm going to leave with this quote from Leslie Lamport. If you want to think about the systems that you're building, you have to think outside of the code, go beyond the code, basically. The code is important. The developer, from a developer point of view, the code is important, but from a system perspective, everything around the code is also at least as important and even more important, because otherwise the code doesn't work very well. And so the key to developing better systems is really getting people to think outside the code and getting the code to work, but getting people to think outside the code. And that's what these abstractions are capable of supporting. That's why abstraction is a very powerful concept, and that can be used to build the right kind of tools and methodologies to make things work. Thank you very much.
Thanks a lot, Sanjiva, for the excellent keynote. So now it's a time we can get a few questions from our audience. Questions?
Thank you. Really, really fun talk, and I really enjoyed it. You gave us a great picture, but it's about enterprise. But you have services also outside enterprise. So I'm thinking of robotic operating system, which is basically a service-oriented architecture. So what do you think about outside of the enterprise, and what is the evolution of services in that context?
So even in robotic systems, my mental model about enterprise is that the interesting part about enterprise is you have many, many different systems that you have to work with. In a robotic platform also you have many systems you have to work with. So I think the service abstraction is very powerful, that can be used for those environments as well. And the same underlying technology of how you manage the abstractions of services, how you create the environment for reuse and modularity and composition are needed even in enterprise architectures. Even in robotic kind of architectures or in-vehicle platforms. So if you think about how doing updates for an in-vehicle platform, modularity plays a key role in being able to safely update stuff. So actually I was talking to somebody yesterday, I heard somebody telling on the plane, on the bus yesterday, that there was one of the flights they were in, they were doing a software update. The plane got delayed by 3 hours because they did a software update and the update failed and they had to back off to the previous snapshot. Right now, you hope that they got backed off correctly, right? Didn't leave a bit of stuff here and there. But that shows you that even in a platform like that, you need this discipline of how do you build and operate software. You need this canary kind of deployment paradigms. You need to be able to back off. There's a lot of things that software is now an essential ingredient in everything. So the discipline of producing software engineering, service computing to me is inherently tied to software engineering. And there's a lot more we can do yet.
Great talk, Sanjiva. Many thanks. I'm fascinated by your contributions to the abstractions that you mentioned. And you are working also in a much larger context in improving the society where you're contributing. So I was wondering, can you speak to your thought process? How can you take these ideas of abstractions to the next level? In other words, how can you provide abstractions for successfully govern communities, societies, and make things better?
Thank you. Very, very interesting question. This guy, Yuval Harari, his Homo sapien book, right? In his book, he talks about the power of the narrative and how stories are used to essentially control populations. And so stories are a form of abstraction. So the power of abstraction is that most people don't want to understand details. Most people want to kind of live in this nice, simple world where everything is nice and simple. That's why it's so easy to manipulate a population, because you can tell a simple story, everybody wants to believe the simple story. And any conflict we have in the world doesn't have a simple story underneath it. It's very complicated, and nobody has time to understand the complexity and the subtlety, right? So the power of abstraction as a way of, so you need to understand that, and that's the thing that a lot of political leaders really understand very well. How to hide all the details and just talk at this massively beautiful level. And then the people who know that, wait a second, that doesn't work, you got to do these things, those are ignored as just noisemakers, they're problem people, right? So I think one of the things that we need to figure out to improve society is how do you get people to understand, first of all, how do you get the right abstractions into the conversation in society? Then second, understand that, okay, with abstraction there are details underneath. And in some things you need to understand the detail. You can't live at the abstraction level. It's very difficult. I don't have an answer for it, but it's an important, very important point. And what struck with me from Yuval Harari's book is that the power of the narrative, that if you tell a good story, people believe it.
Yeah, thank you for excellent presentation. So I would like to consider, ask, how do you consider can large model, enable the automatic abstraction? Yeah, so how do you think about this question? Thank you.
So the question is, how can large language models, can large language models enable automatically creating the right abstractions? The state of technology of large language models today is very much, so again, different opinions from different people. My view is large language models are not intelligent. They're very good at remembering a lot of things. And yes, we could have emerging properties or different concepts of intelligence through that, but they don't understand the problem that they're solving. If you look at computer science abstractions that have done really well, take the simple abstraction of the read-write interface for I/O that Unix has. Right? Unix interfaces with a few APIs for read-write, which have held up over decades now, and have held up for different devices, whether it was tape drives to magnetic disks to SSDs to whatever, it has held up. That abstraction was created by understanding the use cases, understanding the problems, and creating something. So now the question you're asking is very interesting, because what you're asking is, can you take all the information about a company, give it to an LLM, and you tell it saying, generate me the set of atomic service abstractions I need to have. And I don't believe it'll work. I haven't tried it. I don't believe it'll work, because for me, the thing that makes beautiful software still is judgment. Is being able to look at something and say, this is right, this is not right. And that, we can't encode that yet. It's like beautiful architecture in buildings. Beautiful architecture in buildings come from people who know how to, who think in a way that other architects don't think. Right? I can give another analogy. There was somebody yesterday in the talk by the person from Hong Kong, he said there are 70 Michelin star restaurants in Hong Kong. Right? Michelin star restaurant, so you could go to a Michelin star restaurant, you could watch the chef make the food, you could see what ingredients go in, and you could watch him make the food, but when you go home, you can't make the same thing. Right? Because there's an art form to how he or she does it that is not captured in the recipe, in the ingredients. That part, I don't see LLMs being able to capture yet.
So we may have one or two more questions from audience.
Thank you for the presentation. My question is about the thing that you mentioned, that quality, time, and budget cannot be all achieved at the same time. So how do you make this trade-off when you want to start a new project? Which one do you sacrifice?
It's almost always time. Right? Because budget, in large enterprises, governments, budget is always findable, because you've already invested money, so you can't stop it, you keep going. That's why projects just keep on going. Quality, you can't by design sacrifice quality. You end up sacrificing quality as a side effect, because you're under pressure to produce on time. So the first thing that goes is time. That is why nothing ever gets done on time. right? And then as the time deadline comes, you sacrifice quality to get something done. And of course, the budget has already gone by the time you get there. So.
Thank you.
Thank you.
More questions? Okay, thanks again, Sanjiva, for the great keynote. Thank you. So now is a tea break. Please come back to 11 a.m. so we start the second keynote. Thank you.